What's the limit as n goes to infinity of the sum from k is 0 to n of 1 over n choose k? Let's call this thing here something. Let's call it Ln. So we're trying to work out the limit as n goes to infinity of Ln. So what can we say that Ln is at least? Well, if we just take the first term and the last term of this sum, so 1 over n choose 0 plus 1 over n choose n. So obviously every term in this sum here is positive, so I'm just taking the first term and the last term. So that's 1 over n choose 0, which is 1 over 1, plus 1 over n choose n, which is also 1 over 1, which is 2. So Ln is at least 2. Now what I'm going to do is try and provide an upper bound and deal with that as well. So Ln, what I'm going to do now is instead of just taking out the first term and the last term, I'm going to take out the first two terms and the last two terms. So this is going to be 1 over n choose 0 plus 1 over n choose 1 plus 1 over n choose n minus 1 plus 1 over n choose n. So I've taken out the first two and the last two, and let me just add on everything else here. So that's the sum from k is 2 to n minus 2 of 1 over n choose k. So I guess this here is assuming n is at least 2, but since n is tending to infinity, we can assume that. Okay, what is 1 over n choose 0? Well, those are both just 1s again, so we're going to get 2 from that. Now 1 over n choose 1, that turns out to be 1 over n. Same for this guy, so this will be plus 2 over n. And then we've got this sum here. So the sum from k equals 2 to n minus 2 of 1 over n choose k. So ln is equal to this expression here if n is at least 2. So now what we want to do is provide an upper bound for this expression here. First things first, let's think about n choose k. Here's where we're going to use some nice properties about n choose k. Firstly, n choose k is the same as n choose n minus k. This is pretty standard. You can just check this by swapping k for n minus k in this expression here. So that means we can focus on k being less than n over 2. So suppose k is less than or equal to n over 2. So this is a little bit of scrap work on the side here. Okay, what can we do with this? Well, then n choose k is the same as n factorial over k factorial times n minus k factorial by definition. But now there's factorial on the top. Let's simplify this. This can be n times n minus 1 times so on, all the way down to n minus k plus 1. And then I can just multiply that by n minus k factorial, but that will cancel this n minus k factorial here. And so then we just end up dividing this by k factorial. So essentially all I've done is on the top and bottom, I've cancelled out n minus k factorial. Great. So what do we have on the top here? Well, the top here is a polynomial. What's the degree of that polynomial? Well, the degree is just k. So there's precisely k brackets, including this first guy here, on the top. And so that's going to be a polynomial of n of degree k. And k factorial here is just a constant dependent on what k is. The key thing is this is a polynomial of degree k. So if this k was 3, for example, this would be n cubed plus something n squared plus something plus something. It's a polynomial of degree k. Great. So that means when k is less than or equal to n over 2, this is just a polynomial of degree k. If k is bigger than n over 2, what happens then? Well, you can swap k with n minus k, and therefore you'd have a polynomial of degree n minus k. But basically, this thing here is the reciprocal of a polynomial of degree k, or n minus k. But if we look at the range of values of k here, k is going from 2 to n minus 2. So if we look at either a polynomial of degree k or a polynomial of degree greater than k, this thing here is going to be at least a quadratic. So it's going to be at least a quadratic. In fact, the worst case scenario here is if this thing here is n choose 2. And you can just either look at this by Pascal's triangle, but the biggest value, or the smallest value, sorry, that n choose k can be, where k is between 2 and n minus 2, is if k is 2 or n minus 2, in which case this thing here will be n choose 2, and so therefore this expression here is maximized when k is 2. So we can provide an upper bound here and say that this is less than or equal to 2 plus a 2 over n plus, well, how many k values are here? There's n minus 3 of them, times 1 over n choose 2. So you get 2 plus 2 over n plus n minus 3 times 1 over n choose 2. But n choose 2 is just a quadratic, as we said on the side here. And so this thing here will be a linear function divided by a quadratic function. In fact, we could actually just work out what this is. So this is going to be n minus 3, don't need brackets there, n minus 3 over this will be n squared minus n, I think, over 2 as well. But lo and behold, we have a linear function over a quadratic. Now what we can do is apply the limit as n goes to infinity on both sides. So if we call this limit here L, we can say that L is less than or equal to 2 plus 2 over infinity, sort of. In fact, I won't write that. 2 over n, that tends to 0 as n tends to infinity. And this thing here also tends to 0. So this is going to be 2 plus 0, which is 2. So by the sandwich theorem or the kind of squeeze theorem, we have the L from earlier. It was at least 2, but it's also at most 2, and so therefore the limit is 2.